And hello everyone, welcome back to our Turbulence Modeling. We want to continue talking about Kolmogorov length scales and how they affect the cell size. Okay, so we talked about that in the previously, that the ratio of the Kolmogorov length scale to, let's say, a length scale of your interest, that would be on the order of Reynolds number to the -3/4. Okay, so we can estimate the number of cells, and we found that it scales, the number of cells actually scales as a Reynolds number to the 9/4. Okay, so this is actually in the free shear region. For the boundary layer, there will be a different correlation, but let's just do Kolmogorov scaling first. So let's give an example. If you have a 1 meter-ish domain, 1 meter-ish characteristic length scale, and a Reynolds number of 10,000, which is reasonable for turbulence, what is the order of this Kolmogorov length scale? So if you were to substitute eta equals to L times Reynolds number to the -3/4, it will be like as follows. 1 meter times 10,000 to the -3/4, you would get about 0.001 meters or 1 millimeter. This is the rough gauge of the Kolmogorov length scale. So what if the Reynolds number is 2000? Remember, this is a transition Reynolds number for, let's say, a pipe flow, and you will get the Kolmogorov length scale. Okay, 1 meter times 2000 to the -3/4, you'll get about 3 millimeters. 3 millimeters instead of 1 millimeter. Of course, this you can see that this eta actually depends on this domain size or characteristic length scale. Okay, so yeah, that's for the main domain. Okay, for scales closer to the wall, you need to pay more special attention. And for good rule of thumb, okay, what is used in literature, they use these grid lengths in wall scaling units. So in the wall normal direction, you have y plus the grid size to be about, in the dimensionless what do you call it, dimensionless change, delta y plus, it's about 0.05 to 0.5. In the parallel direction, you'll have delta z's, that means in the z direction, and in the x direction, if let's say y was perpendicular to the wall, this would be on the order about 5. So what does this look like? Let's just have a quick drawing, and it will look something like this. So imagine you have, let's say, a wall, and this is y, a distance from the wall. Maybe you use y plus. Okay, so this is 1, 2, 3. Okay, so you would have a grid spacing based on the wall normal. Okay, normal to the wall, you have about 0.5. Okay, or 0.05. Okay, you divide this into 20 pieces, 20 grids. That's really intense for wall modeling. So it's 2 to 20 grids per y plus. It can be that fine. Okay, so that's how thin we are talking about for DNS. You can see why the computational requirements are very high. And what about in the normal direction? I mean the perpendicular direction. You can have, okay, this should be delta x plus or delta z plus is approximately 5. So you have cells looking more or less like this for the DNS boundary layer. Of course, you can have smaller cells near the wall, and then you kind of expand your way as you go up. Alright, so you have the very smaller cells nearest to the wall, you expand it as it goes up, and that's the general rule of thumb. So that gives you an idea on how big or small your mesh should be. Okay, So these are in dimensionless units. So in dimensionless units, you have this as such. Remember, y plus equals to y times the friction velocity. Or is it y times nu? Alright. Sorry, so this is y times z, friction velocity, divided by nu. So this is in meters, this is in meters per second, this is in meters square per second. That should be how we do it. So you have a grid spacing delta y plus, for example, you would just have delta y over u tau, delta y times u tau over nu. Okay, so these are based on wall units, and that is ultimately based on the friction velocity over here. And of course, it'll be good if your friction velocity, you can have a general feel of it, though it's a little bit difficult because you need to take into account the wall shear stress, and actually wall shear stress is a function of, let's say, the friction coefficient, and that itself is some other complicated function of the Reynolds number. So yeah, but near the wall you have to pay attention. It's based on wall units. All right. So now that we know the rough standard for DNS using the Kolmogorov scales, and of course these wall units, we can actually roughly take a look at what the LES and the RANS model, RANS grid spacings look like. Okay, so this is for standard DNS scales, and this will be our reference to compare for LES and RANS. Okay, so and of course always make sure that your Koren number is less than 1 for the best results in stability. So for LES sizing, in this PLDDS paper, one of the papers online from Wang and Chen, the delta y plus is equals to 0.5, whereas for here you can see that it's about 10 times smaller. The smallest cell is about 10 times smaller, and we see, okay, for mixed convection, I mean a typical LES grid, delta x plus equals 40, delta z plus equals 20. This is about 5-ish times, 5 to 10 times this length. So you can see that the LES actually scales about, the grid is about 10 times bigger by the length. Okay, and if you were to look again from another reference, if you're talking about the parallel spacing, okay, if you're talking about parallel spacing from the wall, okay, parallel spacing from the wall, we would have a typical parallel spacing, based on this one, based on this paper, that usually for force flows, okay, this is not that one. For force flows, usually have a boundary layer. Okay, let me phrase that right. Okay, if your boundary layer thickness is equal to delta, then delta x plus is approximately 1 over 10 of delta. Okay, where delta is this boundary layer thickness. So I'm going to do yeah. This is from Spalart's paper. Okay, from Spalart's paper where he talks about the detached-eddy simulation. And he talks about detached-eddy simulation. And okay, so you will have a grid, LES grid. Okay, maybe the smallest will be this. Okay. Okay, for LES grid, the smallest will be about 0.5. So let me use a different color. Smallest will be 0.5 in this direction. Alright, 0.5, and you would have delta x. Okay, again, this is near the wall, right? So it's a bit skewed. So your delta x plus delta y plus, or delta z plus, is approximately 20 to 50. Okay, so actually if you consider the boundary layer, okay, delta x plus, the good guideline is that you take it to be 1/10 of this boundary layer thickness. And for typical boundary layer thickness, you have y plus going up to 500. So that's how thick the boundary layer is if you want to take some ballpark figure. So delta x plus equals to 50 is quite reasonable for LES grid. Okay, so this is about 10 times bigger. So just to give you an idea of scale. Okay, so DNS grid, which is about, let's see, okay, it's about this small. Okay, I don't know whether you can see that. Your LES grid is several times bigger. You can see this blue one. And then what about Reynolds average Navier-Stokes, right? Oh wait, before I go there, I would like to say that because of this, you see that your grid size in the boundary layer is about 10 times that much of DNS. This is a good estimate when you can still have pretty fine resolution. It's about 10 times the grid size. Okay, so whatever you have in DNS, you just scale it up 10 times. Give this a good ballpark figure. So from this you can kind of infer, again by rule of thumb, that the typical LES grid size is about 10 times the Kolmogorov length scale. I mean, this is a ballpark figure, it's not an exact value. So you can kind of infer, based on how you scale the boundary layers, you can scale the LES grid by 10 times the Kolmogorov length scale. That means one LES grid will be able to fit 10 of the smallest eddies in there. Alright, so that's what LES is talking about. Okay, so what about Reynolds average Navier-Stokes? So for Reynolds average Navier-Stokes, we have those with wall functions. Okay, you have those wall functions, and actually you want to place, I mean, it's a good practice to place your first grid, your first wall function grid point at about y equals to 20. Okay, y plus equals to 20. Okay, so y plus equals 20 maybe somewhere here. Giving it a give or take. Y plus. Then you get it about here. Your first grid point will be here. And how about the width? The width of the grid point, or the width of the mesh here. Okay, what is the width of the mesh? For parallel direction, for direction parallel, I mean, I'm talking about this one, the delta x plus, or delta z plus, or delta z plus. What is the width? This one is actually scaling according to the boundary layer thickness. That means it's going to go to about, this size is about, delta x plus will be on the order of 500. Oh, that's pretty big. So 400 to 500. So how big is your first grid spacing of the wall? Okay, let's say for RANS, okay, that's a bad color. RANS grid, Reynolds average Navier-Stokes grid. Okay, so how big would it be? You would have it all the way here, and probably off the page as well. That's how big it is. Okay. Okay, so you have about 20, 40, 60, 80, 100, 120, and you will go off the page, yeah? Off the page. 140, 160. So yeah, you see it's really big. This is your RANS grid size. The smallest grid for Reynolds average Navier-Stokes. You can see the grid is so coarse as compared to, let's say, a DNS or even the LES. So from this, I mean, this is because we have wall functions, right? Okay. Well, it's taking very long to paste, so I'll give it some time. But you can see the difference in the order of magnitude, right? The difference in the order of magnitude is about this much. And then you have 8 to 10 grid points in the log law region. 8 to 10 grid points. 8 to 10 grid points in the log law region. That means your delta y plus, if you consider the delta y plus, I mean the boundary layer thickness to be about 500, 8 to 10 grid points, that means delta y plus equals to 50, which is about 10 to about 100 times bigger than this. Okay, so one good rule of thumb, I mean, okay, this is with wall functions, right? I haven't talked about without wall functions. If you don't, oh sorry, if you don't use wall functions, okay, sorry, computer lagged there for a bit, but anyway, yes, if you don't use wall functions, okay, you have about 5 to 10 grid points from the first point to y plus equals 20. That means this one is with wall functions. If you don't have wall functions, then okay, then you kind of have to split this up to about 10 units here. All right, that means it's looking more like a LES grid. So another 20 to 50 points from y plus equals to 20 to 500. So if you were to take that, then I mean, yeah, your delta y plus will be on the order of 50. Okay, so this is to help you get the accurate boundary layer resolution. Or else if you don't use wall functions, this part you will not resolve at all. Okay, so this is like an order of magnitude estimate for you. Looks pretty good. You can see, oh man, it's no, that don't look too good. Okay, but let me try snipping tool instead. Okay, so this is the snipping tool. Okay, let's paste it down, see whether we get a better quality picture. Oh, yes, yeah. So it's a better picture. It's not great, it's not terrible, but yeah, it is what it is. And yeah, so anyway, yeah, we have if we, let's say we want to have a fully resolved near wall region. Yeah, over here, near wall region for the RANS model. For the RANS model near wall region, we'll kind of have to have a modified Reynolds average Navier-Stokes model to deal with that. And the mesh is about I mean, your mesh sizing here will be about 2 y plus equals to 2 in this y plus less than 20 region. After that, you have a y plus of about 50. So you can see from this order of magnitude estimate that this y plus here equals to 50. So that means this typical RANS mesh is about 100 to 1000 times bigger in terms of length. Okay, the RANS mesh length is about 100 to 1000 times bigger than the Kolmogorov length scale. So if, let's say again, you have Reynolds number 10,000, L is about 1 meter. Okay, so you have this much what do you call that? The Kolmogorov length scale is about 0.001. Then your RANS length scale is about 0.1 meters. You can see that's a very coarse mesh. You just have about 10 points across your whole mesh, and that's it. Okay, so this is just a rule of thumb, just to get you started on the rough length scales that you can have. Okay, so remember how I get it is that I use a Kolmogorov length scale, and I use a rule of thumb to say that if your DNS Y plus is about this much, and going from here to here is about 100 to 1000 times bigger, I would say I will scale the free shear region, the Kolmogorov length scale, and I'll scale it by this same scaling amount, 100 to 1000 times, to get this length scale for RANS, Reynolds Average Navier-Stokes. Of course, this is just an estimate. This is just an estimate that it helps you to get an idea of how big your grid size is. You need to do a little bit more detail. I mean, it's not just the Kolmogorov length scale you have to worry about. You should also, have enough to grid, fine grid. You have a fine enough grid to simulate even the mean flow. Because let's say your Reynolds number is about 2000, and maybe your Kolmogorov length scale is very, very big, maybe even bigger than the domain, for instance. But you may not get let's say you were to use this 1000 times factor over here, you will get your Reynolds average Navier-Stokes number to be about 1 meter. I mean, if you were to use one cell to simulate your entire region, then that kind of doesn't really deal with the proper fluid mechanics of this whole region. I mean, that's just one cell. You need at least it looks from this at least 10. So that you don't just have to deal with the Kolmogorov length scale, but you still have to simulate your mean flow as well. Have a fine enough mesh for that, and that you will need to take consideration when the Reynolds number is somewhat lower. But by and large, for turbulent flow, your Kolmogorov length scale will almost always be smaller. And anyway, for Reynolds average Navier-Stokes, you kind of just simulate all turbulence. Simulate all the turbulence as as viscosity. So you don't really have to care too much about the length scale in terms of Kolmogorov as per se, but you deal more with the so-called flow, the mean flow, and you just need a mesh fine enough to resolve that. That's all you need. But anyway, this is just a ballpark estimate for you. Hope that it will help you to size your mesh a little bit better. Of course, I didn't tell you how to estimate U tau first. Alright, I didn't tell you how to estimate U tau for this y plus coordinate. There are correlations you can use for that. But otherwise, hopefully this shows you how to do it. Give you a ballpark figure for that. So thanks for watching. I'll see you guys again. Bye bye.